Spice Math. That's right. We add it up, multiply it, man. Spice Math. Okay. A couple things we're gonna learn today. Spice Math. All right. Take some time, educate yourself. Spice Math. That's right. You won't believe it's just math. Come on.
Hi, I'm Ruth Doughton.
Hi, I'm Aaron Williams.
Hi, I'm Brandon Alexander.
Hi, I'm Kelvin Doughton.
Hello, I'm Lyndon Sincere.
We are your Spice Math tutors.
You won't believe it's just math. Just math.
Hello again, welcome back to Spice Math. And today we'll be talking about number bases. We're trying to build on base 10 and some of the concepts we shared with you before. And I hope that you get yourselves ready and take your notes. We also want to say a nice shout out to those of you who've been following the program so far. Continue doing so. And don't forget to offer your comments and your critique so we can do this better every time. So, what really is a number system? We've defined that in a previous lesson. And today we're going to look at number bases. The objectives at the end of this lesson, you will be able to define what a number base is, list the digits in a given base, convert from a given base to base 10, and also to convert from base 10 to a given base. Let's proceed. What do you think is a good definition for a number base? Well, some people tend to think that it's a group of digits that we all decide that we're going to use for particular counting purposes. Or it can be defined as a system of counting which uses a particular number of digits. Now in our base 10, which previously we said that the answer was right in your hands, the 10 fingers were used and established as a standard for counting. So, in base 10, the digits that are used are 0, 1, 2, and if you count with me, we can go right up to 9. So these are our 10 digits. Do you see a 10 in that set? Interestingly, there is no 10. And this is base 10. Okay? So the digits that are used in a base usually do not include the name of the base. So in base 10, we're using 10 digits from 0 to 9. And if you add them up, you're actually going to get 10 digits. What do you think we're going to use in base 8? Yes, you are correct. 0 to 7. So just as in base 10, base 8 will not have an 8. We'd have to find a way to write it. And we're going to see that just now. What about base 2? Otherwise known as the binary base, and extremely applicable today in the world of technology and computers. Base 2 would use only zeros and ones, because if you follow the pattern, a base 2 would not have a number 2 or a digit 2. Base 5, like the pattern shows, would be 0, 1, 2, 3, 4. Now comes the interesting question. In base 10, how do we write 10? Well, before the name was coined, you would observe that in order to write 10 in base 10, we would have to go back to the original set of numbers and include 2 of the first set of numbers. That is 1, 10, 0 units. So how do you think we'd write 8 in base 8? 1, 8, and 0 units. How do you think we're going to write 2 in base 2? Yes, you got it. 1, 2, and 0 units. How are we going to write 5 in base 5? Okay, I think by now everybody should have seen the pattern. However, we don't call them 10 once they're in a different base. We'd have to call out the digits one after the other. So if in base 8 we're counting, we'd have to say 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, then 1, 1, then 1, 2, and so on. If you're in base 2 and you're counting 0, 1, 1, 0, 1, 1, and so on. So this number here is not a 10 in base 2. It's 1, 0. In base 5, a similar thing would happen. And in all bases, that is the protocol. Now, why is this so? This is so because each base is built on what you call positional values. If you remember in a previous lesson, we spoke about the Roman numerals and the other methods that were used to count way back in the days before Jesus Christ. Those methods of counting had one flaw. Every time the society became more complex, they had to come up with a new symbol to represent the bigger numbers as they were counting more things and more things. However, in a positional system, as we have seen with base 10, the position of the digit tells you its value. And this concept is commonly known as place value. So in a number in base 10 that says 2025, we see the digits 2 appearing twice, but they're not the same value. The first 2 would be 2 groups of tens, and the other 2 would be 2 groups of thousands, or 2 groups of 10 to the 1 and 2 groups of 10 to the 3 in base 10. So in base 10, we're actually thinking in groups of 10. And this principle follows throughout all bases, which means that if I'm to count in base 2, I'd have to start thinking in groups of 2s. And every time my group is filled, I need to go on to the next position, and so on and so on. If I'm counting in base 8, I'd have to think in groups of 8. And similarly, in base 10, when we think in groups of 10, we can value each column with powers of 10. So in base 8 and 2 and 5 and all the other bases, each position will be valued in powers of its respective base. So let's go to base 5, for example. In base 5, the digits I'll be using would be 0, 1, 2, 3, and 4. Those are the 5 digits. So a number 2, 1, 4 in base 5, we can expand it out based on the position of each digit. But here, we have to be careful because we're not thinking in groups of 10, we're thinking in groups of 5s. So, the first number, which is a 4, will be, what's the base? Base 5 to the power of 0, or units. So that's 4 times 5 to the power of 0. The second number, 1, would be 5 to the power of 1, or 5s. So that's 1 times 5 to the power of 1. And the third number, 2, or the third digit, I should say, is really 2 times 5 to the power of 2, being the third digit. When we did the base 10, the history of base 10, we expressed it in powers of 10. Now we're in base 5, we can express each digit based on its position in a particular power of 5. And that can help us to convert a base 5 number back to a base 10 number. Very simply by multiplying and adding up the sums. Let's see what's happening here. 4 times 5 to the 0, that's 4 times 1, which is 4. 1 times 5 to the power of 1 is 5. And 2 times 5 squared, 5 squared is 25. So 2 times 25 would be 50. And I have almost immediately converted a base 5 number back to base 10 by simply expanding the bases based on the positional value of each digit. 50 plus 5 is 55. 55 plus 4 is 59. We can then say that the number 214 in base 5 is equal to 59 in base 10. By simply using the protocol that we understood from base 10 and its history. We can do the same thing if we had a number written in base 8. Let's see what happens. One, 0, 4. Well, let me put 3. 305. Base 8. What do you think would be the positional value of the 5? It corresponds to 8 to the power of 1. Sorry, 8 to the power of 0. That's usually the first place, what we call units. So it would be 5 times 8 to the power of 0 plus 0 times 8 to the power of 1 plus 3 times what power of 8? 0, 1, 2. Okay, so the pattern continues. As in base 10, we had the powers of 10. Now we're thinking base 8 is going to be powers of 8. Let's do that sum. 8 to the power of 0 is 1. 1 times 5 is 5. 0 times any quantity is 0. And 3 times 8 squared. 8 squared is how much? 64. 3 times 64 is 192. So we get 197 when you sum up 192 and 5. And this is our answer. 305 in base 8 is the equivalent of 197 in base 10. Why don't you try some of these on your own from the explanations that were given and using the expansions and the value of the base? I'm sure you're going to get all of these correct. Okay, so how did you do? Well, let's see if you got the answers correct. The first number, 413 to the base 5, would be 3 times 5 to the 0, since the 3 is in the first column, plus 1 times 5 to the 1, plus 4 times 5 squared. How much is that? 3 times 5 to the 0 is 3 times 1, so that's 3. 1 times 5 to the 1, that's 5. And 4 times 5 squared. 5 squared is 25. 4 times 25 is 100. So that's 100 plus 5 plus 3, that's 108 base 10. Means then that 413 to the base 5 is equal to 108 in base 10. Next one, 2301 base 8. We follow a similar process. 1, this time we're going to do this one going down the page. 1 multiplied by 8 to the 0 plus 0 times 8 to the 1, because we are in base 8 now, plus 3 multiplied by 8 squared plus 2 multiplied by 8 cubed. We're going to have some big numbers coming up here. 1 times 1 is 1. 0 times 8, 0. 3 times 8 squared, that's 3 multiplied by 64, that's 192. And 2 times 8 cubed, that's 1024. And we need to add these up and see what we get. So that's 4 and 2 is 6 and 1 is 7. 2 and 9 is 11. 1 and 1 is 2, and 1. 1,217. So, the number 2301 base 8 is equivalent to 1,217 base 10. Okay? The final one, 1011 base 2. I'm going to work it out over here. So that would be 1 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 squared plus 1 times 2 to the 3. And let's evaluate it. 1 by 1 gives us 1. 1 by 2 gives us 2. 0 by 2, 0 by 4 is 0, and 1 by 2 cubed is 8. Add up, 8 plus 2, 10, and 1, 11. So, the number 1011 base 2 is equivalent to 11 in base 10. Now let's take this up a notch. You've seen how to convert from a particular base to base 10. And we did expansions and multiplication. How do you think we should do conversion from base 10 back to base 8? Or from base 10 back to base 5? Well, you guessed it. If we did multiplication when we converted from base 8 to base 10, we're going back to base 8 from base 10, we're going to have to use repeated division. So let's see if that's going to work. Let's suppose I had the number 125 in base 10 and I need to convert it to base 8. So we're actually doing the inverse. And since we did multiplication to move from base 8 to base 10, we're doing the inverse, we're going to use division. We're going to set it up this way. 125, we're going to divide it repeatedly by 8 and take a note of the remainders, because that's where the result lies, with the remainders. So let's divide. I'm going to call the last column, the remainders. So 8 into 125. 8 into 12, 1, remainder 4. 8 into 45 is what, 5? 5 eighths of 40, remainder 5. Then we divide again by 8, because as I said, it's repeated division until we get a remainder that's less than 8. 8 into 15 goes 1, remainder 7. We can't divide any further because the result we have here is less than 8. So we actually have the answer right here. 175 base 8. So the number 125 or 125 base 10 is equivalent to 175 base 8. Let's see if that is true. Let's take this and try to convert it back to base 10 using the expansions that we did first. So that would be 5 times 8 to the 0 plus 7 times 8 to the 1 plus 1 times 8 to the 2. 5 times 1 is 5. 7 times 8 is 56. And 1 times 8 squared is 64. Let's do the sum. 6 and 4 are 10, plus 5 is 15. 1 and 6 are 7, and 5 is 12. So that's correct. We're getting back the 125 we started with in base 10. So the method of repeated division, when you converting from base 10 to a particular base, actually works. But you have to remember to take a note of the remainders. That's the key. Okay? So in today's lesson, what did we learn? We learned how to define a base. We learned how to count in a base. We learned how to change from base 10, our normal, natural, popular base, into another base, like base 8 or base 2. And then we'll also learn how to change from another base back to base 10. All these processes are there for the taking. It is my hope that as you look at these videos, you are going to take the time and practice these math concepts, because they're going to help you and you will need it. I hope you enjoy your day. Thank you very much.
You won't believe it's just math. Come on. You won't believe it's just math.